Hello dear students, welcome back in the video lecture series. Today we are going to start a new lesson, a new chapter, a new topic for you, and the title is Esr Spectroscopy or EPR Spectroscopy. The Esr or EPR spectroscopy stands for Electron Resonance Spectroscopy, or it is also called as Electron Paramagnetic Resonance Spectroscopy. So electron resonance or electron paramagnetic resonance or electron spin resonance is one of the important property shown by the unpaired electrons, and hence this gives rise to an application in the determination of structures, determination of molecules containing unpaired electron or the substances which are paramagnetic in nature. Okay, so in this lecture we will going to study about some introductory part or basic concepts regarding this ESR or EPR spectroscopy. Okay, and in next few videos which will relate to the ESR or EPR, we will discuss in detail about this a new emerging branch of spectroscopy, that is ESR or EPR spectroscopy. So what is this long form? The long form is very simple: electron spin resonance or electron paramagnetic resonance spectroscopy. So before going to in detail, let us see first of all how a chemical bond is formed. We know that for the formation of a chemical bond we require at least two electrons, and these electrons are either transferred from one combining atom to another combining atom, and when such transfer of electron takes place, there is a formation of ionic bond. So in a bond, in this ionic bond, the two electrons are present, okay, and they are called as paired electron. They are known as paired electron. While in another type of bond we call it as a covalent bond, and that covalent bond is nothing but formed by the formation by the sharing of electrons between the combining atoms. Again, in that covalent bond the electrons are present in a pair. Hence these electrons are known as paired electrons. But some substances are there which may contain unpaired electron, Some chemical species are there, some transition metal species are there, some elements are there which contains unpaired electron in their orbitals. Okay, so orbitals containing unpaired electrons are responsible for giving this ESR spectrum or EPR spectrum. When the substances containing the paired electron, substances which are having paired electron in their structures or in their orbitals, when they are placed in an magnetic field, applied magnetic field, then these substances are weakly repelled, they are slightly repelled. Okay, substances containing paired electron, mind well, paired electron. Okay, so this is the situation, they are containing paired electron in their orbitals, and when such substances are placed in a magnetic field, they are slightly or weakly repelled by that magnetic field, and hence such substances are known as diamagnetic substances. They are known as diamagnetic substances. Okay. On the other hand, some substances containing unpaired electron, at least one unpaired electron is present in their orbitals. Such substances when they are placed in an external applied magnetic field, then they are slightly attracted towards the magnetic field. Okay, such substances are known as paramagnetic substances. Such substances are known as paramagnetic substances. So basically, there are two types of magnetic substances. There are two types of substances on the basis of their magnetic property. Okay, those which are weakly attracted are known as paramagnetic, and those which are weakly repelled by the magnetic field are known as diamagnetic substances. Okay, now there are some naturally occurring paramagnetic substances, means they are containing unpaired electron, and they are naturally occurring O2. So dioxygen molecule is a naturally occurring paramagnetic substance. Okay, then nitric oxide NO, then nitrogen dioxide NO2, and many more transition metal complexes in which the metal atom is having unpaired electron. Okay, so these are all naturally occurring paramagnetic substances, while the artificial means they can be prepared in the reaction mechanism or as an intermediate in the reactions. Okay, so artificially made paramagnetic substances, okay, they are containing generally free radicals. So what are free radicals? So free radicals are the molecules containing unpaired electron. They are known as free radicals. For example, methyl free radical CS3 dot. Okay, this is different. So CS3 plus, this is methyl carbocation. Okay, so this methyl carbocation is 2 electron deficient species. It is found by the heterolytic fission of a single covalent bond. It is called as methyl carbocation. But this species is formed by the homolytic fission or homolysis of a single covalent bond, either between CC bond or by the CX bond or CH bond, anyone. Okay, so these are containing a single electron or a odd electron containing species, or a molecule with a unpaired electron. Such species are known as free radicals, and these free radicals are artificial chemical substances which are paramagnetic in nature. Okay, means if they are placed in an external magnetic field, they are weakly attracted, and hence they are called as paramagnetic substances. Now we know that the electron in an atom having two motions, and these two motions are known as orbital motion and spin motion. Okay, so electrons are the basic fundamental particles of an atom, and these electrons are not stationary, they are continuously revolving around the central nucleus. Okay, they are negatively charged. All these property we are aware about, that electrons carry charge, that is -1 charge, then they are also having some mass. Okay, though the mass is very less, but they are having some mass. So these are the some basic properties. Along with that, these electrons are having two types of motions. These electrons are having two types of motions. And due to these two types of motions, one is called as orbital motion and another is called as spinning motion. Spinning motion in an axis around its own axis. Okay, so suppose this is a central nucleus of an atom, okay, and these are the shells or orbits around this central nucleus, okay, and here in this nucleus protons and neutrons are present, and in these orbits or shells electrons are continuously moving. In the first shell 2 electrons, in second 8, etc. Okay, so these electrons are continuously revolving around these orbits, so that motion is called as orbital motion. And due to this orbital motion, the electron is giving rise to orbital motion. It gives rise to orbital angular momentum. So due to this orbital motion of the electron around the central nucleus, an angular momentum is generated. This is an angular motion, and due to this angular motion, angular momentum is generated, and that angular momentum is called as orbital angular momentum. Okay, next motion is that spinning motion of that electron. So while revolving around the nucleus is also continuously spinning. About its own axis, like this. There are two motions of the electrons, as I already told you that this is one orbital motion, and due to orbital motion there is a angular momentum known as orbital angular momentum. The second motion is called as spin motion. Okay, and the electron is spinning about its own axis, either in clockwise or in anti-clockwise direction. Okay, and these motions are simultaneous motions. Okay, but when we consider singly the spinning motion of that electron, the spinning motion of that electron is gives rise to an angular momentum. It is called as spin angular momentum. That spinning motion gives rise to spin angular momentum, and it is nothing but the intrinsic property. Of that electron, and hence it is called intrinsic spin angular momentum. Okay, then these are about the angular momentum. Now due to these two motions, different motions of that electron, the two magnetic moments are possible. And these magnetic moments are known as one magnetic moment is arising from the orbital motion of the electron, and another is arising from the spin motion of the electron. Okay, the strength of the magnetic moment, the strength of the magnetic dipole is expressed in terms of magnetic moment. Okay, strength of the magnetic dipole. Strength of the magnetic dipole is expressed in terms of magnetic moment. Okay, so this magnetic moment is nothing but this is the strength of magnetic dipole. Okay, so that dipole is generated due to the motion of electron, and the motions are of two types, orbital and spin motion, and due to these two types of motions, two magnetic moments can be possible. Okay, and in most of the cases means about 99.9% cases, only the spin magnetic moment is to be contributed in the total magnetic moment of an electron. In the total magnetic moment of an electron, what is the contribution of the orbital magnetic moment? It is very less, or it is very close to zero. Means that, what is the another statement that we can say? The total magnetic moment of an electron is due to the only spin magnetic moment, and the spin magnetic moment arises due to the spinning motion of that electron. Okay, so this is all about the some atomic structure part that we have learned up to BSc level. Okay, and this, our next point of discussion is the some basic concepts or basic theory which is required to study for the understanding of Esr spectroscopy, Okay, now for the system which contains only one electron, such as for hydrogen atom. So hydrogen atom is having only one electron, its atomic number is 1, so Z is equal to 1, and hence E is equal to 1. The total spin quantum number S, total spin quantum number S, it is denoted by capital S, is nothing but it is given by summation of SI. So what is SI? So it is the vectorial sum of the individual spins of all electrons present in that system, present in that substance. Okay, and this is nothing but the total spin quantum number of that chemical species or that chemical substance. Total spin quantum number S is equal to summation of, it is a vectorial sum, means you have to consider the direction, which is either clockwise, anti-clockwise, having plus sign, minus sign, etc. Okay, so it is a vectorial sum of all the spins, of all the electrons present in that system. Okay, and the S can take the integral values, zeros or half integral values. Okay, so S may be 0, S may be 1/2, it may be 1, it may be 3/2, it may be 5/2, it may be 3, it may be 2, etc. So the total S value, the total spin quantum number S may takes the value like this. Okay, now the magnitude of spin angular momentum, magnitude of spin angular momentum is given by S is equal to under root of S into S plus 1, under root of S into S plus 1 into H upon 2 pi, okay, or this under root sign is nothing but raised to 1/2, so we can write S into S plus 1 total raised to 1/2 into H upon 2 pi, means the magnitude of spin angular momentum is the integral is in the multiples of H upon 2 pi, where H is Planck's constant. And the value of H is 6.6 6.64 into 10 raised to minus 34 joule second. 6.64 into 10 raised to minus 34 joule second. Okay. Then magnetic spin quantum number ms. Magnetic spin quantum number. Magnetic spin quantum number. Okay, we know that there are 4 quantum numbers, that is known as principal quantum number, then azimuthal quantum number or orbital quantum number, then magnetic quantum number and spin quantum number. Okay, this magnetic spin quantum number ms can take the values of 2s plus 1, can take the values of 2s plus 1 values. Okay, varying from s to s minus 1, s minus 2 up to minus s. Okay, so how many values are possible for magnetic spin quantum number ms? These values are given by, the total number of values are given by 2s plus 1. So 2 into total spin plus 1, these are the magnetic spin quantum number ms, and they can be taken the values s minus 1, s minus 2, s minus 3 up to minus s values. Okay, then the components. Now we have to study about what happened actually when we place the chemical substances or chemical species which are having the total spin s is equal to 1/2 and total spin s is equal to 1. Okay, if such chemical species, if we place in an external applied magnetic field, then what will happen for the ms values? Okay, so what are the possible values of ms when we place the chemical species or substances having s is equal to 1/2 and s is equal to 1? That we have to study here. Okay, so for s is equal to 1/2, the situation is like this. This is B. So the B stands for applied magnetic field. B stands for strength of magnetic field. Okay, so here the possible ms values for s is equal to 1 are 2 into 1/2 plus 1. Okay, so by the formula 2s plus 1, so s is equal to total spin is equal to 1/2. So how many possible values are there? 2 into 1/2. So 2 get cancelled, 1 plus 1, it is equal to 2. Okay, so the two ms values are possible for total spin s is equal to 1/2. Okay, and these are s minus 1, s minus 2 up to minus s. So what is s? S is equal to plus 1/2. S is equal to plus 1/2. Now only two values are possible. So these intermediate values are not possible here. So only plus 1/2 and the last one is minus 1/2. Only these two values are possible for ms, and hence we can write for s, for capital S is equal to 1/2, that is total spin quantum number s is equal to 1/2. Two values are possible only, and these are plus 1/2 and minus 1/2. Okay, so this can be shown like this. Okay, so here this is plus 1/2 ms values and this is minus 1/2 values. This is minus 1/2 values. Okay, so this is the applied magnetic direction of applied magnetic field, and the splitting of the ms values is into two states, that is minus 1/2 and plus 1/2. Now for capital S is equal to 1, for capital S is equal to 1, so what are the possible, how many possible values are there for ms values? It is given by 2s plus 1, so 2 into 1 plus 1, that is equal to 2 plus 1, that is equal to 3. So 3 values are possible for ms. How many total values are possible? Only 3 for s is equal to 1. Now how many these 3 values are? Which are these 3 values? These are s minus s. Okay, so s is 1 and minus s is minus 1. Okay, so in between 1 and minus 1 there is only one number, and that is 0. Okay, so 1, 0 and minus 1, these are the 3 possible states for total spin s is equal to 1. So this is the direction of magnetic field. Okay, so this is ms, and splitting of this ms takes place into 3. So this is 0, this is plus 1, and here it is minus 1. Here it is minus 1. So plus 1, 0 and minus 1. These 3 states are possible for the capital S is equal to 1. Okay, and here from this formula we can calculate the possible number of ms values for the given total spin of the chemical species. Okay, now the magnetic moment generated from an electron spin, the magnetic moment is generated, and it is related to the spin angular momentum. Okay, and it is given by the equation mu is equal to g into EH upon 4 pi m into bracket of under root s into s plus 1 bracket complete h upon 2 pi. Okay, so this is the equation. Okay, and its z component means its value or its magnitude along the z direction, x, y, z, the 3 coordinate axes are there, and hence the magnitude of this along the z direction will be given as mu z is equal to minus g into EH upon 4 pi m into ms, and it is equal to minus g be into ms. Okay, so this is mu z. So what is this g? This g is called as a constant for electron, and that is called as Landé splitting constant. Landé's splitting constant. Landé splitting constant. Okay, the negative value suggesting that the charge of electron is negative. Okay, and here this g value is also called as g factor, simply g factor. G factor or Landé splitting factor is same for a single unpaired electron. For single unpaired electron, the value of g is equal to 2.00 2.00232. 2.00232. Okay, here in this equation the Be is called as Bohr magneton of electron. Be stands for Bohr magneton. Bohr magneton for electron. Okay, and here Be is equal to Eh upon 4 pi m. Okay, this equation mu z, that is z component of magnetic moment, okay, can also be written as mu z is equal to gamma e into h upon 2 pi gamma e into h upon 2 pi into ms. Okay, so this is the equation for magnetic moment along the z direction. Okay, so this gamma e stands for gamma e is equal to magneto-gyric ratio. It is also called as magneto-gyric ratio or gyromagnetic ratio. Okay, and this ratio is a characteristics property of a given chemical substance. Okay, so this is all about the introduction and some basic concepts which are required to study for the understanding the concept of ESR and EPR spectroscopy. Okay, ESR or electron paramagnetic resonance spectroscopy. Okay, so this is all about the today's video. Okay, so I think you enjoyed this video and thanks for watching and have a nice day.